In this video we're going to look at ways in which we can extend the results about the binomial expansion that we met in Unit 1 to deal with cases where the power that we're raising the expression to is not a positive integer power. Now at Unit 1 we saw that if we've got 1 plus x to the power n, where n is a positive integer, then we can expand the expression as 1 plus nc1 times x plus nc2 times x squared plus nc3 times x cubed, all the way along general terms ncr x to the r, and then the term terminated with x to the power n. You'll also have observed that nc1 is the same thing as just n, nc2 is the same thing as n times n minus 1 over 2 factorial, that nc3 is n times n minus 1 times n minus 2 over 3 factorial, and so on. And as we said, when n is a positive integer, then the expansion terminates with the x to the n term, and the expansion is valid for any value of x. Now what we're going to do in this video is to investigate whether the expansion 1 plus x to the power alpha, which if our Unit 1 results are true, ought to be the same as 1 plus alpha times x plus alpha times alpha minus 1 over 2 factorial x squared plus alpha times alpha minus 1 times alpha minus 2 all over 3 factorial times x cubed, and so on. And what we want to do is determine whether or not this expansion is valid in cases when alpha is not a positive integer. Now we should note that if alpha is not a non-negative integer, then this expansion will have an infinite number of terms. In other words, the expansion will not terminate. So let's start off by considering the case when alpha is a half. If we've got alpha equals a half, then the expansion that we've got for 1 plus x to the power alpha becomes 1 plus x to the half equals 1 plus a half x plus a half times a half minus 1 over 2 factorial x squared plus a half times a half minus 1 times a half minus 2 all over 3 factorial x cubed plus a half times a half minus 1 times a half minus 2 times a half minus 3 all divided by 4 factorial times x4 plus lots more terms. Tidying up these first few terms though, we get 1 plus x to the half is 1 plus a half x minus an eighth x squared plus a 16th x cubed minus 5 128ths x to the 4 plus higher terms. But at the moment we don't know whether this expansion is valid or not. So what we're going to do is we're going to have a look at the graph of y equals 1 plus x to the power a half, together with the graph of the approximations to 1 plus x to the half, which are 1 plus a half x, 1 plus a half x minus an eighth x squared, 1 plus a half x minus an eighth x squared plus a 16th x cubed, and so on. So we're going to look at the approximations given to us by the first few terms in the expansion, and we're going to use GeoGebra to do that. So here we can see that we have got the graph in red is the graph of 1 plus x to the power a half, and what we've got in blue is the linear approximation, which was just 1 plus a half x. So let's have a look what happens if we start taking more terms in the expansion. So at the moment we've got the case when n equals 1. The series expansion for 1 plus x to the half gives us a quadratic approximation of 1 plus a half x minus an eighth x squared. And we can see from GeoGebra that this is a good approximation over most of the interval from minus x equals minus 1 through to x equals 1. But it is pretty hopeless outside that interval. The cubic approximation to 1 plus x to the power half provided by the expansion is 1 plus a half x minus an eighth x squared plus a 16th x cubed. And we can see again that this is a good approximation to the function for values of x between minus 1 and 1, but outside those values it is a pretty hopeless approximation. Looking at the approximation obtained by taking the terms up to x to the power 4 in the expansion of 1 plus x to the half, we see a similar pattern. It's a good approximation between minus 1 and 1, but ceases to be a good approximation away from those values. Let's see now what happens if we add even more terms from the series. And you can see that adding even more terms of the series really doesn't change the overall pattern. And the overall pattern is that the expansion for 1 plus x to the power half is valid for values of x satisfying minus 1 is less than x is less than 1. Let's now consider a second case. We'll consider the case when alpha equals minus 2. And when alpha equals minus 2, the expansion 1 plus x to the power alpha equals 1 plus alpha x plus alpha over alpha minus 1 over 2 factorial x squared, etc. becomes 1 plus x to the minus 2 equals 1 minus 2x plus minus 2 times minus 3 over 2 factorial x squared plus minus 2 times minus 3 times minus 4 over 3 factorial x cubed, and so on, which simplifies to 1 plus x to the minus 2 equals 1 minus 2x plus 3x squared minus 4x cubed plus 5x to the power 4. And again, we're going to use GeoGebra to see whether this is a valid expansion or not. So here in red again is the graph of 1 plus x to the minus 2, and at the moment on screen we have the graph showing the linear approximation taken by just the first two terms of the series. And if we turn the video on now and set the animation going, we can see that when n equals 2, the approximation is not dreadfully good over a large range. N equals 3, it's better. N equals 4, it's better again. N equals 5, okay. And as we get larger and larger values of n, the approximation is getting better and better over an interval of minus 1 to 1. However, outside the interval of minus 1 to 1, the approximation obtained from the series is nowhere near the function itself. So we can say that it looks as if the series 1 plus x to the minus 2 is 1 minus 2x plus 3x squared minus 4x cubed plus 5x to the 4, etc. is valid provided the value of x lies between minus 1 and 1. One final example to consider is the case when we have alpha equals 1.6. With alpha equals 1.6, the expansion for 1 plus x to the alpha becomes 1 plus 1.6x plus 1.6 times by 0.6 over 2 factorial x squared plus 1.6 times 0.6 times minus 0.4 over 3 factorial x cubed, etc., which simplifies to 1 plus x to the 1.6 equals 1 plus 1.6x plus 0.48 x squared minus 0.064 x cubed plus 0.224 x to the 4. And again, we can use GeoGebra to see whether this expansion looks as if it is valid. So setting the video going. We can see that as we increase the value of n, then the approximation becomes increasingly good for values of x between -1 and 1, but outside those values the approximation is of very little value. So this suggests then that the series expansion for 1 plus x to the power 1.6 is valid provided the value of x lies between -1 and 1. Putting our experiences from these three examples together, we can draw the conclusion that the expansion for 1 plus x to the power alpha is valid for a value alpha which is not a positive integer, provided x lies between -1 and 1. So that concludes our introductory investigation into the extension to the binomial expansion.